Tonight, on Space Science, the story does not begin on the Moon. It begins far above Earth, in the silent space between worlds, where NASA is slowly building the path that could turn brief missions into a permanent human foothold, at the lunar South Pole, among endless shadows, frozen water, and harsh light. The Artemis program is preparing for something far greater than a landing. It is laying the groundwork for a real moon base, step by careful step. If this journey into humanity's next frontier sounds fascinating, please like the video, subscribe to Space Science, and settle in. Far from the lunar ground, the first shape of a moon base begins in the large, quiet region around the Moon, rather than on the surface itself. NASA does not begin by placing a permanent settlement directly onto the dust. It begins by building a way to reach the Moon again and again with enough control, enough cargo, and enough safety that surface work can become routine instead of rare. In this outer region, the Moon is not yet a place of buildings, wheels, and habitats. It is a destination inside a broader system of motion. That system includes Earth, the space between Earth and the Moon, the paths that spacecraft follow, and the vehicles that can survive those paths. Before any base can exist, this wider environment must become usable. The Moon sits close by in astronomical terms, yet it remains difficult to reach. The distance from Earth to the Moon is about 384,000 kilometers on average, which is small beside the scale of the solar system, but large enough to demand careful planning. A mission to the Moon is not a straight climb upward. It is a transfer through deep space, shaped by gravity, fuel limits, radiation exposure, communication delay, and the need to return. Every kilogram carried outward matters. Every system must keep working after launch stress, vacuum, temperature swings, and days of travel. In this way, the outer region around the Moon acts less like empty space and more like an environment with its own rules. NASA's Artemis program approaches this environment as an architecture rather than a single flight. An architecture is a planned set of parts that work together over time. Instead of one spacecraft doing every job, different elements divide the work. Some carry crew, some carry cargo, some help with landing, some support operations near the Moon. This matters because a moon base cannot be built in one attempt. It must emerge from repeated missions that deliver people, equipment, and supplies in stages. The outer region therefore becomes the first construction zone, even though no walls rise there and no dust is disturbed. The construction is logistical before it is physical. At this outer level, Earth remains the source of almost everything. Launch vehicles lift hardware out of Earth's deep gravity well. Factories on Earth build life support systems, power units, landing equipment, communication hardware, and scientific tools. Training happens on Earth. Mission control remains on Earth. Medical support, engineering analysis, and most spare capacity remain on Earth as well. This means the earliest form of a moon base is not a cluster of structures at the lunar pole. It is a chain that starts on Earth and stretches outward. The lunar base depends first on the reliability of that chain. The crew vehicle called Orion belongs to this outer system. Orion is built to carry astronauts beyond low Earth orbit and back again. It is not the moon base itself, and it is not designed to be a permanent home. It is a transport craft meant to protect its crew during launch, travel, and return. In the outer region of Artemis planning, such a vehicle is essential because it makes the journey repeatable. Repetition is the real beginning of permanence. A base is not defined only by structures on the ground. It is defined by the ability to keep arriving, keep working, and keep returning with lessons that improve the next mission. Cargo matters just as much as crew. A moon base requires much more mass than a short landing mission. Surface power systems, mobility systems, habitats, scientific instruments, spare parts, and consumable supplies all demand transport capacity. Some of these loads may travel with crew missions, but many must move separately. This creates a basic principle for lunar settlement. People alone do not build outposts. Freight does. In the outer region, then, the key question is not simply whether astronauts can reach lunar space. It is whether useful hardware can be delivered there in the right order, in working condition, and in enough quantity to support later layers of activity. Time also changes meaning in this region. A mission to the moon unfolds over days, not hours, and the schedule is shaped by launch windows, orbital conditions, spacecraft readiness, and surface goals. Communication between Earth and the moon is fast enough for conversation support, yet not instantaneous in the sense of direct physical help. A crew near the moon cannot rely on rapid rescue in the way crews in low Earth orbit often can. This creates a stronger need for independence, redundancy, and fault tolerance. Redundancy means having more than one way to perform a vital function. Fault tolerance means the system can continue working even when one part fails. These ideas are quiet in description but decisive in design. A base can only grow from missions that assume distance is real. Radiation is another part of the outer environment. Beyond much of Earth's magnetic shielding, spacecraft crews face a harsher particle background from the sun and from high-energy particles that move through deep space. Short missions can manage this risk with shielding, mission timing, monitoring, and operational caution. But longer campaigns increase the importance of protection and planning. The base that appears later on the lunar surface is partly a response to this outer reality. Surface stays need shelter. Transit needs reliable protection. Mission length is never a simple matter of desire. It is shaped by the conditions between worlds. In this outer region, orbital mechanics quietly governs everything. Orbital mechanics is the science of motion under gravity. It determines how a spacecraft leaves Earth, approaches the moon, circles it, meets other vehicles, and returns home. These paths are not merely lines drawn for convenience. They are chosen because each path carries trade-offs in fuel use, timing, stability, and access. The early stages of Artemis reflect this truth. NASA's goal is not only to touch the moon, but to create a framework in lunar space that can support many later missions. Before habitats can be unloaded or surface routes explored, the paths above the moon must become familiar, tested, and dependable. This is why the outer region remains the proper beginning for the story of how NASA will build a moon base. At this distance, the base exists first as coordination. It exists as launch cadence, mission design, mass budgets, navigation, and transport reliability. It exists as the patient linking of Earth systems to lunar objectives. Nothing here looks like a settlement in the ordinary sense. There are no pressurized rooms on the surface, no parked rovers, no storage berms of dust, no racks of tools waiting near an airlock. Yet all of those later things depend on what happens here. The empty black between Earth and the moon is the first territory that must be mastered, because it is the corridor through which every later structure, every machine, and every human presence must pass. By treating cislunar space, the region between Earth and the moon and around the moon, as an operating domain rather than a brief crossing, NASA changes the meaning of lunar exploration. The effort becomes less like a sequence of isolated expeditions and more like the gradual opening of a route. Once a route becomes dependable, presence becomes possible. Once presence becomes repeatable, infrastructure begins to make sense. In this outermost region, the moon base is still invisible. It exists only as intention supported by engineering, but intention, when made durable through repeated access, is the first material of settlement. In lunar orbit, the broad corridor of access begins to narrow into a place of pause, exchange, and support. Here the outer path toward the moon becomes more structured. Spacecraft no longer only travel past the moon or descend directly toward the surface. They begin to gather around a planned orbital presence that can organize later work below. This is where NASA's concept of Gateway takes shape. Gateway is not the base on the moon. It is an outpost in lunar orbit, a small station meant to support repeated missions deeper into the lunar environment. In the gradual logic of building a moon base, this orbital outpost stands between transport from Earth and activity on the ground. Gateway is planned as a modular station, meaning it is made of separate pieces joined together in space. This approach fits the larger Artemis method. A permanent surface base is not placed all at once, and neither is its orbital support system. Modules are launched separately, brought to lunar orbit, and connected over time. The structure is intended to remain much smaller than the International Space Station, but its purpose is different as well. It is not meant to host large crews for long, uninterrupted occupation in the early stages. Instead, it serves as a staging point, a communications node, a logistics platform, and a place where crews and cargo can pass through on the way to the lunar surface and back again. The orbit chosen for Gateway is important because lunar space is not uniform. Some orbits around the moon are low and fast, close to the surface and useful for certain observations, but they require regular control to maintain. Others reach much farther out. Gateway is associated with the near rectilinear halo orbit, a long looping path shaped by the combined gravity of Earth and the Moon. The name is technical, but the basic idea is simple. The orbit is elongated and stable enough to reduce fuel demands for station keeping, while also giving useful access to the lunar polar regions. The station does not hang motionless over one point. It moves along a repeating path that brings it nearer to the moon at one part of the loop and farther away at another. That motion is part of the design. This orbital position matters because NASA's surface plans are centered on the South Pole region of the moon. A station in lunar orbit must therefore do more than exist. It must support surface missions where they are most likely to occur. Gateway helps connect arriving spacecraft, landing systems, and surface operations into one coordinated pattern. Crew vehicles from Earth can reach the station. Lunar landing systems can also operate with it as part of the broader mission design. Supplies may pass through it. Data may pass through it. Mission planning may treat it as a place where operations can be organized before a descent begins or after a return from the surface is complete. The first practical value of Gateway is logistical. Logistics is the organized movement and support of people, supplies, and equipment. A moon base depends on logistics more deeply than on any single machine. Surface systems wear down. Spare parts are needed. Consumables such as food, air processing materials, scientific equipment, medical supplies, and maintenance tools must be replenished. An orbital outpost can help manage this flow. It can receive equipment launched from Earth and prepare it for later use. It can provide temporary storage. It can support inspection and transfer operations that would otherwise have to be compressed into short mission timelines. In this way, the empty concept of access begins to gain structure. Power is one of the first demands on any orbital station. Gateway's design includes power and propulsion as a foundational element. Power supports communications, guidance, internal systems, thermal management, and visiting vehicles. Propulsion allows the station to maintain and adjust its orbit when needed. These are not dramatic functions, but they are central. A station without steady power becomes inert. A station without control of its motion cannot remain useful in the long term. In a lunar architecture aimed toward building a moon base, even quiet orbital systems carry great weight because every later mission relies on their stability. Communications are another vital role. The lunar poles, especially the South Pole, create complicated lines of sight. Terrain can block direct radio contact, and surface operations may not always maintain a clear connection with Earth. An orbital platform can help relay information. This includes routine voice traffic, engineering data, navigation support, and scientific results. Communication is not only convenience, it is coordination, safety, and timing. A moon base cannot function if vehicles, habitats, and crews operate as isolated islands. Gateway helps reduce that isolation by tying orbital and surface activity into a shared system. Gateway also has meaning as a test environment. Missions farther from Earth demand systems that can operate with greater independence and over longer periods. An outpost in lunar orbit allows engineers and mission planners to test equipment, procedures, and habits of work in deep space before those same methods are relied upon more heavily on the surface or in later missions toward Mars. Life support, docking routines, remote maintenance, crew scheduling, and response to technical faults can all be studied there. The station becomes a bridge between exploration by visit and exploration by sustained presence. Yet Gateway has limits, and those limits are important to the realism of the moon base story. It is not planned as a complete answer to lunar settlement. It does not replace the need for reliable landers. It does not remove the harsh conditions of the lunar surface. It does not provide the broad living volume of a large orbital station, nor does it itself create local resources. It remains a support element. Its value depends on the whole architecture around it, including launch systems, crew transport, landing systems, and the surface hardware that will one day form the beginning of a base. If those other elements do not arrive in sequence, Gateway alone does not become a settlement. For that reason, Gateway is best understood as an orbital tool for continuity. Artemis is not aiming only for a flag and footprints pattern of exploration. It aims for campaigns, meaning linked missions that build on one another. Campaigns need memory in hardware form. They need a place where systems can accumulate function over time instead of starting fresh with every arrival. Gateway provides part of that memory. It remains in lunar space as missions come and go. It gives persistence to an environment that otherwise would be crossed only briefly. In doing so, it helps turn lunar space into an operational neighborhood, rather than a distant destination visited one mission at a time. Within this orbital region, the future moon base still remains below and not yet visible. No habitat walls stand on the ground. No dust roads connect one installation to another. But the structure of support is becoming clearer. The path from Earth now has an intermediate anchor. That anchor is modest in size, but large in consequence. Gateway brings order to the region above the moon. It gathers transport, power, communications, and timing into one orbiting framework. By doing so, it makes the next layer of the lunar presence more practical. The moon base, still absent from sight, begins to acquire an address in space before it acquires a footprint on the surface. From lunar orbit, the next inward region is not yet a built site, but the broad surface zone where NASA intends to place the first repeated human landings. This is the South Pole region of the Moon. In current Artemis planning, this area matters because it offers a rare combination of scientific interest and practical value. It is not gentle terrain, and it is not simple terrain, yet it appears more promising for long-term human presence than many other parts of the Moon. Here the idea of a moon base begins to move from orbital support toward actual ground. The question is no longer only how to reach the Moon, but where repeated arrival can become the beginning of settlement. The lunar South Pole is not a single flat point at the bottom of a globe in the way a map may suggest. It is a rugged region of craters, ridges, slopes, and elevated ground shaped by ancient impacts. Because the Moon's axis is only slightly tilted, sunlight reaches this polar landscape at a very low angle. The sun circles near the horizon instead of rising high overhead, as it does at many places on Earth. This low-angle light changes everything about the region. It creates long shadows, strong contrasts, and a patchwork of brightness and darkness that can remain stable for long periods. In the broadest sense, the South Pole is chosen because this unusual light environment may support repeated operations better than equatorial regions that pass through long, harsh nights. NASA does not treat the entire polar region as equally suitable. The interest lies in certain areas near the South Pole where landers can approach, crews can work, and nearby resources may be accessible. This is why the region is often discussed in terms of candidate landing zones, rather than one final permanent point already fixed beyond change. The exact locations for future missions remain subject to engineering assessment, surface data, mission goals, and evolving hardware capability. What is known is that the South Pole offers conditions that align with long-term planning. What remains uncertain is the final shape and exact arrangement of a full base, because that will depend on what early missions actually find and how well systems perform. One reason for this regional focus is access to sunlight on elevated ground. Some ridges and crater rims near the pole receive light for longer portions of the lunar cycle than most other places on the Moon. These are not places of constant daylight in the absolute sense, but they may offer repeated periods of illumination that are valuable for power generation and thermal control. For a future base, this is important because energy drives almost every surface function. Solar panels need exposure. Equipment survives more easily when temperature swings are moderated. Work becomes more manageable when power interruptions are less severe. The South Pole is therefore not chosen because it is easy. It is chosen because, within a difficult world, it may be less difficult in ways that matter. Another reason is proximity to permanently shadowed regions. Some craters near the pole are so deeply shadowed that sunlight may not have reached parts of them for very long spans of time. These areas are extremely cold, and observations indicate that water ice may exist there, mixed with lunar soil or preserved in other forms. That possible presence of water matters greatly for a moon base. Water supports life directly, and may also be processed into oxygen and hydrogen, which are useful for breathing systems and, in principle, for propellant production. Yet this promise remains a matter of investigation rather than settled abundance. Observations indicate polar ice is present in some form, but it remains uncertain how concentrated, how accessible, and how easily extractable it will prove to be at the scale needed for sustained human operations. The South Pole also offers scientific richness. Ancient cold traps may preserve records of the solar system's past in the form of frozen volatiles, which are substances that can change easily into gas, such as water, carbon dioxide, ammonia, and other compounds. The geology of the region may also expose material of interest from deep impacts and long lunar history. For NASA, this means the chosen region supports both habitation goals and scientific goals. A moon base is not planned only as shelter. It is also a working site where field science becomes part of the daily purpose of presence. The South Pole makes this combination possible in a way that is especially compelling. Yet the region is not welcoming in a simple human sense. The low sun angle can help with long-duration lighting in some places, but it also creates severe visual difficulty. Shadows stretch across the surface and can hide slopes, rocks, and sharp changes in ground shape. Temperature conditions remain difficult, especially where shadow dominates. Navigation is more complex. Surface operations must account for limited lines of sight, uncertain soil behavior, and the challenge of landing safely in rough terrain. This means that choosing the South Pole is not a claim that the region is benign. It is a judgment that the region's advantages may outweigh its hazards when compared with other lunar environments. For the logic of building a moon base, the South Pole acts as a compromise between survival needs and resource hopes. Equatorial regions of the moon are easier to picture because they are more familiar from many past images and missions, but they also face long lunar nights that last about 2 Earth weeks, placing heavy demands on stored energy and thermal protection. Polar regions change that balance. They do not remove hardship, but they may reduce certain burdens while offering access to scientifically and operationally valuable deposits. This is why Artemis planning keeps returning to the South Pole. The region gathers several essential needs into one place, even if none of them are fulfilled perfectly. Approach to this region also shapes mission design. Landers must be able to target difficult terrain with increasing precision. Surface systems must tolerate cold, dust, and shifting light conditions. Communication links must be maintained despite terrain blockage and low-angle geometry. Mobility systems must be ready for slopes and interrupted visibility. In other words, once the South Pole becomes the destination, many other design choices follow naturally from that decision. The region does not passively receive the base. It actively determines the form that the base must take. In this stage of the journey inward, the moon base remains a future arrangement rather than a visible settlement. The South Pole is still a selected environment, not yet a cluster of structures, but this choice marks a major narrowing of intent. The broad moon becomes one specific region. The mission stops speaking about lunar presence in general and starts speaking about a place with distinctive light, cold, terrain, and possibility. Here the first ground truth of Artemis begins. Before power systems are placed, before habitats are assembled, before wheels leave tracks in the dust, the region itself must be chosen. NASA's plan places that choice at the South Pole, where the moon offers its most demanding and most promising threshold for a permanent foothold. Within the South Pole region, the next inward layer is not the solid ground itself, but the pattern of light that falls across it, and the darkness that remains, before any structure can be placed, before any route can be trusted. This shifting balance of illumination must be understood. At the lunar pole, light is not arranged in the familiar daily cycle known on Earth. The sun does not climb high into the sky and then sink below a distant horizon. It stays low, circling near the edge of the landscape. Because of this, the land receives light in a thin, glancing way. Hills, crater rims, small rises, and shallow depressions all gain unusual importance. A modest change in elevation can decide whether a place spends long periods in light or long periods in shadow. This low-angle sunlight defines the broader environment in which a moon base must first survive. NASA's polar plans depend in part on the existence of places that receive sunlight more often than most of the lunar surface. These areas are sometimes described as zones of extended illumination. The phrase does not mean perfect, endless daylight. It means that over long spans of time, Some elevated ground near the pole may receive repeated sunlight with shorter interruptions than equatorial regions endure. That distinction matters. The Moon rotates slowly relative to the Sun, and most places on its surface face about 2 Earth weeks of daylight followed by about 2 Earth weeks of night. At the pole, however, the geometry changes. There, some places may avoid the full burden of this cycle. For a future outpost, this pattern of partial but frequent light is one of the strongest practical reasons to work near the pole. Solar power depends on exposure, and on the Moon, energy is not a secondary concern. It is the center of surface survival. Life support systems need power. Communication systems need power. Scientific instruments need power. Thermal regulation needs power. Charging vehicles needs power. Heating components that would otherwise become too cold may require power. Even the simple act of keeping sensitive electronics within safe operating limits depends on energy. A site that receives more regular sunlight can support smaller energy reserves than a site that must endure a longer, deeper darkness. The difference can shape the whole mass and complexity of a base. Yet the light at the pole is difficult even when it is useful. Because the Sun stays near the horizon, it casts long shadows across the surface. A rock can throw a dark line much longer than would be expected under a high sun. A gentle slope can become visually confusing because one side is bright while another disappears into blackness. The land gains contrast but loses clarity. Edges may appear sharper than they are. Depressions may hide entirely. Surface navigation becomes harder because vision depends not only on brightness, but on the angle at which brightness arrives. In this environment, a crew or a vehicle may face a scene that seems half erased. The horizon itself can feel uncertain, not because the terrain is unknown in principle, but because low light reduces the number of clear visual cues. This matters for landing as well as for later work. A lander descending toward the pole cannot rely on the broad, even lighting that helps define terrain in many equatorial images of the Moon. Instead, it faces a field of stretched shadow and glare. Sensors, guidance systems, and terrain mapping become especially important. The spacecraft must distinguish safe ground from slopes, rocks, and crater edges under conditions where the human eye alone may not judge depth well. In this sense, polar light is both resource and hazard. It offers the possibility of usable energy while simultaneously making the approach to that energy more difficult. The long persistence of shadow is the other half of this region. At the pole, darkness is not merely the absence of light during a passing night. In some places, it becomes an enduring environmental condition. Deep crater interiors and certain depressions may remain shaded for extremely long periods because the low sun never rises high enough to cross their rims. These permanently shadowed regions are among the coldest known places in the solar system. They attract great interest because water ice and other volatiles may survive there. But in this section, the focus remains on the light pattern itself. The important point is that the South Pole is not one coherent lighting zone. It is a mosaic. One ridge may receive regular sunlight. A nearby hollow may receive almost none. The base cannot be planned as though the whole landscape shares one simple day. This mosaic forces site planning to become very exact. A difference of a few meters in elevation may affect how often solar panels receive light. A habitat placed slightly too low may lose useful illumination that a nearby ridge would have provided. A communication mast may need a particular crestline to keep contact paths open. A route between two work areas may be manageable during one interval of light and difficult during another. This means that lunar-based design at the pole is not only about selecting a general region, it is about tracing the fine relationship between sunlight and topography across that region. light becomes a map layer as important as the ground itself. Thermal conditions follow this pattern closely. Sunlit areas on the Moon can become very warm relative to shadowed ones because there is no substantial atmosphere to spread heat. At the pole, where shadows can persist and sunlight arrives at a low angle, the contrast can be especially strong over short distances. A machine crossing from light into shadow may face a fast change in thermal environment. Materials expand and contract with temperature. Batteries behave differently in cold. Lubricants, seals, and joints can become harder to manage. Human operations must also respect these transitions, since spacesuits and equipment must keep internal conditions stable even when the outside environment changes sharply. Thus, the pattern of light is not just something seen, it becomes something felt in every system. For a future base, light conditions also influence human rhythm in a place that has no natural Earth-like day. Crews depend on clocks, artificial lighting, and scheduled activity rather than on sunrise and sunset in the ordinary sense. Still, external light matters psychologically and operationally. A landscape in low, constant angle light does not offer the reassuring cycle familiar to terrestrial life. Instead, it presents long visual sameness interrupted by technical windows of opportunity. Work periods may be arranged around illumination at specific sites, not around a natural morning or evening. The environment teaches that time on the Moon is organized by engineering need rather than biological expectation. In the inward movement of this story, the South Pole now appears less as a point on a lunar map, and more as a living pattern of brightness and darkness. The Moon Base cannot simply occupy this pattern. It must adapt to it with care. Light will tell NASA where power can be gathered, where landers may descend more safely, where routes can remain practical, and where the edge of useful ground gives way to cold obscurity. Shadow will indicate where caution deepens, where temperatures fall, and where hidden resources may lie beyond immediate reach. Before the builders touch the dust itself, they must first read this quiet arrangement of low sunlight and enduring darkness, because the first true design of a polar outpost is written in the movement of light across the land. After the broad pattern of polar light and shadow comes the ground that receives it. In this region, the future Moon Base meets the actual shape of the lunar surface. The South Pole is not a smooth plain waiting quietly for equipment to arrive. It is a broken landscape made by impacts over immense spans of time. Crater rims rise and curve. Shallow ridges connect one height to another. Slopes lean into shadowed hollows. Rock fragments lie across the soil at many scales, from fine grains to large boulders, even before habitats, power systems, or vehicles are considered. This terrain imposes its own order. It tells engineers where a lander may touch down, where a structure may sit safely, and where movement may become slow or uncertain. The first fact of this ground is roughness. Roughness does not only mean a dramatic cliff or a deep crater wall, it also includes the countless smaller changes in height and texture that affect stability. A surface may appear level from orbit and still contain hidden irregularities that matter to landing legs, wheels, and foot travel. At the lunar South Pole, low-angle sunlight can exaggerate or conceal these details, making them harder to judge by sight alone. For a moon base, this means that terrain study must be exact. Maps of elevation, slope, rock abundance, and local relief become part of the construction process before any piece of hardware arrives. Slopes are especially important because nearly every activity depends on ground that can bear load without shifting. A lander needs a surface that is not too steep, or else its structure may tilt beyond safe limits during touchdown. A habitat needs stable placement so that internal systems, docking points, and pressure boundaries remain secure. A vehicle needs routes that do not demand too much traction or risk sliding on loose soil. Human movement in a spacesuit also becomes more tiring and less precise on uneven ground. On Earth, the body unconsciously relies on air resistance, familiar gravity, and ordinary balance cues. On the Moon, gravity is weaker, and motion changes with it. A person can carry loads more easily in some ways, yet momentum behaves differently, and footing on slopes becomes a larger concern. The polar landscape offers useful high ground, but useful does not mean simple. Ridges may receive better sunlight and broader lines of sight, which can help with power generation and communication. Yet ridges are not broad roads. They may narrow, break, or descend into rough transitions. Their surfaces may contain scattered rocks, shallow undulations, and patches of softer soil. A promising crest for one purpose may be awkward for another. A place that supports solar panels well may not suit repeated vehicle crossings. A route that seems direct may prove inefficient if it crosses too many small depressions or unstable edges. This is why planning for a base begins not with the idea of one perfect point, but with a network of workable surfaces whose qualities differ from one another. Crater rims near the South Pole receive special attention because some may combine elevated illumination with access to nearby shadowed regions. In broad planning terms, such locations appear attractive. They may allow a base to stand in comparatively favorable light while remaining close to scientifically valuable and potentially resource-rich cold traps. But crater rims are not uniform rings with even safe top surfaces. They are old impact structures altered by later impacts, erosionless weathering from micrometeoroid bombardment, and the slow churn of surface material. Their edges may be sharp in one place and softened in another. Their slopes may steepen unexpectedly. Their soil thickness may vary. A rim can be both promising and dangerous at once. This brings the story inward to lunar dust and soil, called regolith. Regolith is the blanket of broken rock and mineral fragments that covers much of the Moon. It forms over very long time spans as impacts shatter surface rock into smaller pieces. At the finest scale, parts of it resemble powder. At coarser scales, it contains grit, pebbles, and larger fragments. It is not soil in the biological sense because it contains no living matter and no weathering by air or water like Earth soil. But for engineering purposes it acts as the immediate ground that receives force. Wheels press into it, landing exhaust disturbs it, boots sink into it, structures rest upon it. The behavior of regolith is therefore central to how NASA will build any lasting presence. One challenge is that regolith is abrasive. The grains are not rounded by water or wind. Many are angular and sharp at microscopic scales. During the Apollo missions, lunar dust clung to suits, scratched surfaces, and worked its way into joints and seals. Artemis planning takes that experience seriously because a base requires many more repeated contacts with the surface than short visits did. Dust stirred by landing plumes may travel outward at high speed and settle over equipment. Dust carried into airlocks may accumulate over time. Mechanical parts exposed to repeated dust contact may wear more quickly. Optical surfaces, radiators, connectors, and suit interfaces all need protection from gradual contamination. On a moon base, dust is not an occasional nuisance. It becomes part of daily life. Regolith also behaves differently depending on thickness, compaction, grain size, and local slope. In some places it may support weight well. In others it may give way more deeply under wheels or feet. A rover route that seems manageable in one lighting condition may become risky where loose soil lies over a slope. Even small slips matter because repair opportunities are limited and damage can spread through a mission system. A vehicle stuck or tilted on rough ground is not merely delayed. It may threaten the schedule, the safety margin, or the use of a landing zone. For this reason, terrain trafficability, the ability of ground to support movement, becomes a key measure in base planning. Landing itself changes the surface. Rocket exhaust interacting with regolith can erode, scatter, and accelerate dust and small particles. This process may reshape the uppermost layer of the landing area and expose harder material below, though the exact effect depends on engine design, thrust, altitude, and local soil conditions. Repeated landings near a base therefore create a need for separation, protection, or later surface preparation. The future moon base cannot assume that untreated dust will remain harmless under regular traffic from landing systems. Over time, the landscape around a landing zone may need to be managed as carefully as any built structure. Boulders and block fields add another level of difficulty. Fresh impact debris may remain angular and uneven. Even when large rocks are sparse within a selected landing area, smaller blocks across nearby routes can damage wheels, slow travel, or complicate cargo movement. A habitat site may seem favorable in broad topographic terms and still require careful clearing or avoidance of rock hazards. Because launch mass is limited, Earth-moving capability on the Moon will likely begin small. This means the earliest phases of base building must adapt to the terrain more than they reshape it. The ground is accepted first, then gradually modified where practical. In this terrain region, NASA's moon base is still only beginning to touch the surface in concept. The essential lesson is quiet but strict. The South Pole will not be built upon as if it were a blank platform. Every ridge offers advantage mixed with constraint. Every slope asks whether weight, traction, and stability can be trusted. Every layer of dust waits to interfere with machinery while also preserving the record of the Moon's long history. Before the base can draw power, collect ice, or shelter crews, it must first find firm footing in a landscape that resists simple occupation. The shape of the ground is therefore not a background detail. It is one of the first true builders of the base, because it determines what kind of human presence the Moon will allow. Close to the ridges of longer light and beyond the edges of safer working ground lie the darkest parts of the polar landscape. In the inward movement of a future moon base, this is the next region of concern. These are the permanently shadowed areas near the South Pole, often found inside craters or in depressions whose interiors the low sun cannot reach. Here the story turns from visible terrain toward hidden material. The ground remains lunar regolith, but its thermal history is different from that of nearby illuminated surfaces. Because sunlight may never directly warm these places, they can remain extremely cold for very long periods. That persistent cold makes them important. It allows volatile substances, materials that can readily turn into gas when warmed, to remain trapped near the surface. Among them, water is the most significant for human exploration. The promise of lunar ice is one of the strongest reasons that the South Pole is linked to long-term habitation. Water matters in the plainest way because people need it. Yet on the Moon, water also matters because it can be divided into oxygen and hydrogen. Oxygen can support breathing. Hydrogen and oxygen together can also serve as ingredients for propellant if produced, stored, and handled with the right infrastructure. In this way, water is not only a consumable supply, it is a potential foundation for local industry. A base that can use local water would depend less completely on transport from Earth. This is one of the deepest ambitions in Artemis planning. even though it remains partly an ambition rather than an achieved capability. Observations from orbit strongly suggest that water ice exists in some polar regions of the Moon. Instruments have detected signs consistent with hydrogen-bearing material and with surface or near-surface frost in specific conditions. Radar studies, neutron measurements, thermal modeling, and impact observations all contribute pieces to this picture. Together they indicate that cold traps near the poles can preserve water and other volatiles over long spans of time. What they do not yet fully resolve is the exact form, abundance, distribution, and ease of extraction at the scales that a working base would require. Water may exist as grains of ice mixed through regolith, as coatings on particles, as more concentrated deposits in some places, or in combinations of these states. The difference matters greatly for engineering. A small amount of water spread thinly through large volumes of soil is not the same as a thick, concentrated deposit. Both are scientifically important, but they do not offer the same practical value. If the ice is sparse, much more material must be excavated, heated, and processed to recover a useful amount. That increases power demand, equipment wear, and operational complexity. If the ice is patchy, then prospecting becomes more important because the base must identify where effort will produce worthwhile returns. If the ice lies beneath a dry upper layer, excavation depth becomes part of the challenge. Thus, the mere presence of water is not enough. A base needs usable water at a useful rate. The cold itself creates difficulty. Permanently shadowed regions may stay at temperatures so low that ordinary surface systems perform poorly or fail without careful protection. Electronics, batteries, mechanical joints, wiring, and sensors all behave differently in extreme cold. Some become brittle, some lose efficiency, some require continuous heating simply to remain functional. A rover operating from a brighter ridge into a shadowed crater does not merely cross into darkness, it crosses into another thermal world. This means that cold traps cannot be treated like simple supply depots waiting nearby. Reaching them, working within them, and bringing material back out may demand specialized systems more robust than those used in sunlit terrain. Light conditions add another layer of difficulty. In permanently shadowed regions, cameras and human vision cannot rely on sunlight. Illumination must come from artificial sources, active sensors, or reflected light from distant terrain, and reflected light may be weak and unreliable. Navigation becomes more deliberate. Surface texture, slope, and obstacle detection all require instrumentation that can work without natural brightness. Dust and loose soil remain present there as well, though hidden in darkness. A machine entering such an area must therefore solve several problems at once. It must see, stay warm enough to function, retain power, and avoid becoming trapped in terrain that may be poorly understood at fine scale. For these reasons, the earlier stages of an Artemis Moon Base are not likely to depend immediately on large-scale extraction from deep shadow. Instead, the likely pattern is gradual. Robotic scouting, local sampling, thermal mapping, and targeted experiments would help determine which deposits are accessible and worth developing. Small demonstrations of extraction may come before broader use. This cautious sequence follows the larger Artemis method. The Moon is approached as a place where repeated missions build knowledge step by step. In the case of ice-bearing cold traps, that patience is especially necessary because the gap between promising observations and routine industrial use is still large. Still, even limited access to polar volatiles could change the logic of a base. Imported water is heavy. Every kilogram launched from Earth carries cost in mass, energy, and mission planning. If even part of a base's water need can be met locally, the surface outpost becomes less like an isolated campsite supplied entirely from afar and more like a growing settlement that begins to interact with its own environment. Local use of water would also influence where infrastructure is placed. A habitat might remain on better lit, safer ground, while transport routes and processing equipment connect it to nearby resource zones. This would create one of the first functional relationships between different parts of the polar landscape, one area for steadier living conditions, another for extraction, and the paths between them for regular movement. Cold traps also matter scientifically apart from their practical value. Because they preserve volatiles under extreme cold, they may contain records of delivery from comets, asteroids, the solar wind, and possibly volcanic outgassing from the moon's past. Those records may be layered or mixed in ways not yet fully understood. A moon base near such regions would provide repeated human and robotic access to these archives. Yet in this section, the scientific interest remains secondary to the central issue of building. The key point is that the base's deeper inward logic begins here. The moon is no longer only a place where structures may stand. It becomes a place where local material may one day support those structures and the people inside them. Because uncertainty remains, NASA's future base cannot be designed around the assumption of immediate abundance. It must be able to function even if extraction proves slower, harder, or less productive than hoped. This is an important scientific and engineering discipline. Observations indicate opportunity, but they do not guarantee easy use. A realistic base plan treats lunar ice as a strong possibility to be tested and developed, not as a magical solution that removes the need for imported supplies. In that restraint lies the difference between exploration and fantasy. At this inward stage, the polar moon reveals one of its quietest and most consequential features. Near ridges of useful light, there are pockets of enduring darkness where history, chemistry, and practical survival may meet. NASA's moon base will likely stand outside these cold traps rather than within them, but it will orient part of its purpose toward them. The outpost will need the safer ground and steadier light of nearby elevated terrain, yet its long-term promise will be tied to what the darkness may hold. In this way, the hidden ice-bearing regions do not merely sit beside the future base. They help explain why the base belongs at the pole at all. Once a future outpost is placed on workable ground near useful light and within reach of polar resources, the next inward requirement is energy. A moon base can endure rough terrain, cold horizons, and long supply chains only if power remains steady. On the lunar surface, power is not one system among many. It is the system that allows the others to exist in active form. Air circulation, water processing, internal heating, communications, computing, lighting, charging, scientific work, and maintenance all depend on it. Without steady energy, a habitat becomes a sealed shell that slowly loses function. A vehicle becomes stored mass. A scientific instrument becomes silent. In this sense, the base begins to feel truly alive only when electrical power moves through it. At the lunar South Pole, power planning starts with sunlight, but sunlight there is unusual. It arrives at a low angle and does not fall evenly across the land. Some elevated areas may receive light during large portions of the lunar cycle, while nearby depressions remain dark. This makes solar energy attractive but also demanding. A base cannot simply spread panels in any direction and assume a reliable daily pattern. It must choose locations with care, often on ridges or rises where illumination returns more often. The position of the sun near the horizon means that panels may need to be arranged to capture light coming from a shallow angle rather than from high overhead. Even the shape and orientation of the local ground affect how much useful energy can be collected. Solar power is likely to be one of the earliest and most practical energy sources for Artemis surface operations, because sunlight is available without imported fuel, and solar systems are already well understood from long use in space. Yet the South Pole teaches that solar power on the Moon is not simple abundance. Dust may settle on surfaces and reduce performance. Low light angles may change efficiency. Terrain may cast shadows across equipment at critical times. Periods of darkness still occur even in the more favourable polar zones. Because of this, a base must treat solar energy as a resource to be captured carefully, stored deliberately, and distributed with discipline. Energy storage is therefore inseparable from energy collection. When sunlight weakens or disappears, stored power must carry the base through the interruption. This storage may take the form of batteries or other systems designed to hold energy for later use. The principle is familiar from everyday life on Earth, but the lunar version is harsher. Storage systems must survive vacuum, radiation, abrasive dust, and wide temperature changes. They must deliver power reliably when sunlight falls away, and they must do so without adding too much mass to the launch burden from Earth. A battery that is safe, durable, and efficient on Earth may still require redesign for long service on the Moon. Here again, the base depends on repetition. Power storage is not only for one landing period, it must support mission after mission and endure many cycles of charging and discharge. This leads to a basic balance that shapes the whole outpost. A base with more solar exposure may need less stored energy, while a base with less favourable exposure must carry greater reserves. More reserves mean more mass, more thermal management, and more system complexity. Less reserve means greater vulnerability during darkness or equipment failure. The design of the power system therefore becomes a constant negotiation among geography, hardware capability, safety margin, and mission duration. The base is not built first and powered second. Its very size, schedule, and layout are set by what the power system can support. Distribution is the next quiet problem. Generating energy at one point is not enough if habitats, charging stations, science instruments, and work areas lie some distance apart. Cables, connectors, switching equipment, and control systems must carry electricity where it is needed without excessive loss or excessive fragility. On Earth, power distribution is often hidden in walls, buried lines, or protected grids. On the Moon, it is part of exposed infrastructure. Lines may cross dusty ground or connect modules that are added gradually over time. Connectors must work despite contamination risk. The system must also allow isolation of faults so that one failure does not disable the entire outpost. A moon base cannot depend on a single unbroken line of power, with no graceful way to reroute or protect essential loads. Essential loads are the devices and systems that must remain active even during difficulty. In a lunar habitat, these include life support, thermal control, pressure monitoring, communication links, and core computing. Other systems, such as some scientific instruments or certain charging tasks, may be reduced or delayed during low power periods. This means the power architecture must do more than supply electricity. It must rank priorities and preserve the most important functions first. The outpost survives not merely by having energy, but by knowing how to spend it. In a limited environment, every watt is a decision. Thermal control is deeply bound to the power system. Lunar equipment does not sit in a gentle outside climate. In sunlight it may warm quickly, in shadow it may become intensely cold. Habitats, batteries, electronics. and mechanical systems often need active heating or cooling to stay within safe operating limits. This requires power even when no obvious work is being done. A quiet base at rest still consumes energy simply to remain healthy. The result is that the true power demand of a moon base includes not only visible activity, but also invisible preservation. Much of the electricity may go toward preventing systems from drifting out of survival range. Because sunlight is variable and storage adds mass, NASA and its partners have also considered the longer-term possibility of nuclear surface power. A small fission system could, in principle, provide steady energy through darkness and reduce dependence on local illumination. This idea is scientifically and technically plausible, but for Artemis surface operations it remains part of a developing path rather than an established working element on the Moon. That uncertainty matters. A realistic account of base building cannot assume that compact nuclear power will simply appear and solve the polar energy problem. It may become important in time, especially for larger and more demanding outposts, but the timing, exact design, and operational role remain subject to development and testing. This uncertainty keeps solar-based planning at the center of near-term thinking. The base must be able to function with what is more immediately achievable, while also leaving room for later growth if additional power systems become available. This creates a layered energy strategy. Early missions may rely on smaller arrays, careful site selection, disciplined scheduling, and moderate storage. As the base grows, power generation and storage can expand. New modules, charging demands, extraction equipment, and longer stays will all increase the need. In this way, the power system does not arrive fully complete. It grows with the outpost, and the pace of that growth helps determine how quickly the base itself can become more capable. Power on the lunar surface is therefore not only about technology, it is about tempo. It sets the rhythm of work, the safe length of occupation, the amount of equipment that can run at once, and the confidence with which crews can move beyond immediate shelter. A moon base with modest power remains cautious and local. A moon base with abundant stable power becomes broader in reach and steadier in routine. For NASA, building an Artemis base means first learning how to make polar energy dependable in a place where sunlight is partial, darkness is meaningful, and every unit of stored electricity carries the weight of survival. Once power becomes reliable, the outpost ceases to be a temporary camp protected by luck and timing. It begins, quietly, to act like a permanent place. With power flowing across the outpost, the next inward system is connection. A moon base cannot function as a cluster of isolated machines and shelters. It must be able to send information, receive instructions, share status, guide movement, and maintain awareness of where people and vehicles are located. On the lunar South Pole, these needs are shaped by distance, terrain, and the absence of the familiar navigation framework used on Earth. There is no ready-made lunar equivalent of a complete global positioning system waiting overhead. There's no atmosphere to carry ordinary radio behavior in the same way people experience on Earth. There are only spacecraft, relays, antennas, clocks, sensors, and the strict geometry of the Moon itself. In this environment, communications and navigation become one combined foundation of daily control. The first part of that foundation is communication with Earth. Even a small outpost depends on a steady flow of information moving between the surface and mission teams at home. Engineering data must travel outward from the base so that ground specialists can monitor system health. Voice and video links may support crew operations, science activity, maintenance, and medical consultation. Commands may travel inward towards surface assets or orbiting support systems. Scientific data, navigation updates, weather information about solar activity, and planning products all join this exchange. The base may stand on the Moon, but much of its situational awareness remains distributed across Earth-based teams and systems. At the South Pole, direct communication with Earth is not always simple. The Moon keeps the same face toward Earth, but the polar regions sit near the edge of that visible hemisphere, and local terrain can block line of sight. A ridge may help one antenna see the sky while a crater wall hides another. A rover descending toward shadowed terrain may pass out of direct contact if the geometry turns against it. This means a base cannot rely only on one straight radio path from habitat to Earth. It needs a layered communication approach, with some links direct when possible, and others relayed through orbiting infrastructure when direct contact is weak or unavailable. This is one reason gateway and other lunar communication concepts matter. An orbital relay can help carry information between the surface and Earth, while also connecting vehicles and systems operating near the Moon. The idea is not simply to make conversation easier. It is to create continuity. A future moon base needs communication that persists through changing terrain angles, shifting mission locations, and the growing number of machines working at once. As Artemis expands, the Moon will not remain a place where one crew and one lander operate alone. Multiple assets may share the same broader region. That makes coordination more demanding and turns communications into infrastructure rather than mission decoration. The next part of the problem is local communication within the base zone. Habitats, power equipment, surface vehicles, scientific stations, and visiting landers all need to exchange data. Some links may be by radio, others may use wired systems for stability and protection from interference or obstruction. The exact mix may change with the maturity of the outpost, but the principle is stable. A base must know its own condition from moment to moment. Pressure readings, temperatures, power levels, battery state, environmental control status, equipment faults, and suit system health all need to be tracked and shared. The communications network becomes the nervous system of the settlement. Without it, the base loses the ability to sense itself clearly. Navigation is closely tied to this network because movement on the Moon cannot depend on the effortless location awareness that many people experience with Earth-based digital devices. Lunar navigation must be built more deliberately. Position, navigation, and timing together form the broader discipline. Position means knowing where an object is. Navigation means determining how to move from one place to another. Timing means keeping systems synchronized with accurate clocks, which is essential because many forms of ranging and signal interpretation depend on precise time. On the Moon, all three must be developed through a combination of orbital support, onboard sensors, terrain knowledge, and networked signals. For the earliest Artemis surface operations, navigation will likely combine pre-mapped terrain, inertial guidance, visual hazard detection, and communication links with orbiting and Earth-based assets. Inertial guidance means the use of internal sensors to estimate movement by measuring changes in motion. It is powerful but accumulates error over time, so it works best when corrected by external references. Visual systems can compare observed terrain with stored maps. Altimeters and range sensors can help measure height and distance. Orbital relays and standardized lunar communication frameworks may eventually strengthen this process by providing more regular positioning services. The goal is not merely to help a rover avoid getting lost. It is to support precise landings, repeated route use, coordinated surface traffic, and safer operations near difficult terrain. Timing may sound abstract, but it quietly underlies the whole system. Signals used for ranging and navigation depend on accurate measurement of when information is sent and received. If clocks drift too much, position estimates grow less reliable. If different systems do not share timing well, communication and coordination become less robust. On Earth, people rarely notice this hidden structure because established networks handle it in the background. On the Moon, an Artemis base must help build that background almost from the beginning. Reliable timekeeping becomes part of reliable presence. A future lunar communications and navigation framework is often described in terms of interoperability. This means different systems built by different organizations can still work together through shared standards. That is especially important for Artemis because NASA is not acting alone. International partners, commercial lander providers, robotic missions, and later surface services all need ways to exchange data and coordinate movement without each mission reinventing the entire structure. A moon base becomes stronger when its communications and navigation systems are not isolated inventions tied to one short mission, but parts of a broader lunar operating environment. Standardization may sound quiet and bureaucratic, yet it is one of the true enablers of permanence. The polar landscape makes local positioning especially valuable. Long shadows can obscure landmarks. Repeated work near crater rims or around equipment fields creates a need for precise route knowledge. A rover carrying cargo to a habitat, a crew returning from an ice prospecting site, or a lander approaching a known zone all benefit from navigation that is more exact than simple visual judgment. Precision reduces wasted travel, lowers risk, and helps preserve confidence in surface planning. The more the base grows, the more important the precision becomes. A lone expedition can improvise some of its movement. A functioning outpost cannot afford constant improvisation. Communications also shape safety in a direct human sense. Spacesuit excursions depend on continued contact with the habitat and with mission control support. Health status, suit consumables, route timing, and emergency response all rely on good links. If a person or vehicle disappears behind terrain without adequate relay support, the risk rises quickly. A moon base therefore needs communication not only where it is easy, but where trouble is most likely. This often means investing in relay capability and network discipline before expansion becomes comfortable. In this inward layer of the base, communication and navigation transform the outpost from powered shelter into coordinated presence. Energy keeps systems alive, but connection tells them how to act together. It tells the habitat where the rover is, tells the rover how to return, tells Earth what the surface is experiencing, and tells a descending spacecraft how to find its way into a difficult polar landscape. On the Moon, to know where one is and to remain in contact are not conveniences added after survival. They are part of survival itself. NASA's future Artemis base will therefore be built not only with metal, insulation, and power lines, but with routes of information and time that allow the settlement to understand itself as it grows. Once the outpost has power and a working network of communication and navigation, the next inward layer is motion across the nearby surface. A moon base cannot remain only a fixed shelter surrounded by a narrow walking circle. Even a modest outpost needs the ability to move tools, inspect equipment, carry samples, reach promising ground, and return without exhausting the crew. This is where early surface mobility becomes essential. In NASA's Artemis planning, that first widening of range is closely tied to the Lunar Terrain Vehicle, an unpressurized rover meant to help astronauts travel farther from their landing area and conduct more science than they could on foot alone. It is not the final form of lunar transport, and it is not a moving home. It is the first practical machine that turns a fixed foothold into a local operational zone. Walking on the Moon remains possible, but walking alone sets strict limits. A suited astronaut can only travel so far before time, energy, suit consumables, and safety margins begin to narrow. The polar terrain adds further difficulty with slopes, rough regolith, low-angle light, and scattered obstacles. Carrying scientific tools by hand, bringing collected material back, or reaching multiple work sites in one excursion becomes more demanding under those conditions. A rover changes this balance. It allows more distance to be covered without spending the crew's strength on the act of movement itself. This matters because a moon base grows not only by what it shelters, but by what it can regularly reach and use. The Lunar Terrain Vehicle is planned as a human-rated unpressurized rover. Human-rated means it is designed to carry people safely in the intended operational environment. Unpressurized means it does not provide a shirt-sleeve cabin like a spacecraft or habitat. The crew would still wear spacesuits while riding and working. This distinction is important. The vehicle expands range, but it does not remove the exposure and operational discipline of surface activity. It sits closer in spirit to a work rover than to a travelling room. Its value lies in mobility, cargo carrying, scientific support, and repeated use over difficult ground rather than in long-term crew shelter. NASA's public framing of the Lunar Terrain Vehicle emphasizes that it should let astronauts go farther and do more science in the South Pole region than earlier lunar explorers could manage. The rover is also intended to support remote operation without a crew at times, which is a subtle but important feature. A machine that can work robotically between crewed visits becomes more than transport. It becomes part of the persistent infrastructure of the outpost. It may inspect equipment, reposition cargo, support scouting, or remain active when no astronauts are present on the surface. This makes the vehicle one of the first systems that helps the base outlast any single crew stay. In the earliest stage of a base, local mobility likely begins with modest goals. The rover would carry astronauts from the habitat or landing zone to nearby scientific sites, infrastructure points, and terrain features selected for study. It might transport tools, spare parts, sample containers, portable instruments, and maintenance equipment. It could also help inspect power arrays, communication stations, or route markers spread around the outpost. Even such ordinary tasks matter greatly. A fixed installation becomes easier to maintain when people are not forced to walk every distance while burdened by gear. On the Moon, efficiency is not a luxury. It directly affects safety, productivity, and the number of useful tasks that can fit inside a surface mission. Cargo movement is one of the rover's quietest but most important roles. A moon base grows by accumulation. New equipment arrives. Broken parts must be replaced. Scientific samples must be transported. Tools must move outward for fieldwork and come back inward for reuse. An unpressurized rover does not solve every cargo challenge, especially for very large loads, but it offers the first general-purpose surface transport capability. That capability changes how planners think about site layout. Once movement becomes easier, equipment does not all need to be clustered tightly in one spot. The base can begin to spread into functional zones while still remaining connected through routine travel. The polar environment shapes the rover's design and use at every level. Wheels must handle loose regolith, uneven slopes, and abrasive dust. The suspension and chassis must tolerate repeated vibration over rough ground. Power systems must operate in low temperatures and changing light conditions. Controls must remain usable by astronauts wearing bulky gloves. Surfaces exposed to dust must resist wear and contamination. Visibility systems must help crews judge terrain under low-angle sunlight and deep shadow. None of these requirements are dramatic in themselves, yet together they define whether daily mobility becomes dependable or frustrating. A moon base cannot afford a rover that works only in ideal conditions, because ideal conditions are not the polar norm. Range is another major factor. A rover increases how far astronauts can travel from immediate shelter, but every outward kilometre also raises the importance of route planning, energy budgeting, and emergency response. On Earth, a vehicle breakdown may bring inconvenience. On the Moon, it can produce an urgent operational problem. The vehicle therefore has to be treated as part of a support network, rather than as an independent machine. Communications, navigation, suit planning, spare components, and route discipline all travel with it in practice. The more the base depends on mobility, the more the rover becomes woven into every other system already described. NASA has also approached lunar mobility through commercial partnerships, rather than assuming that the agency itself will simply own and operate every surface vehicle in the traditional way. Publicly, the Lunar Terrain Vehicle has been framed as a service model involving industry, with companies developing and providing capabilities for Artemis missions. That approach fits the wider pattern of Artemis, where commercial partners support transport, cargo delivery, and other parts of the architecture. For the moon base, this has an important consequence. Surface mobility is being developed not merely as a one-off mission accessory, but as a service that could persist, improve, and support repeated use over time. Science also pushes the rover beyond the role of simple transport. NASA has selected instruments intended for the Lunar Terrain Vehicle, including tools meant to study surface composition and scout for potential resources. This means the rover itself becomes a moving scientific platform. Instead of merely carrying astronauts to a work site, it may help identify promising ground while in transit, extending the scientific awareness of the base across a wider area. A vehicle that can both transport and observe adds efficiency to every excursion, and helps turn local mobility into a form of exploration. Still, early surface mobility remains local by nature. The rover widens the base's reach, but it does not yet create true independence from the outpost. The crew still depends on habitat support, airlock return, and suit limits. The vehicle still operates inside a carefully planned radius shaped by energy, time, terrain, and rescue considerations. This is why it belongs at this stage of the inward path. It is the first widening of action around the base, not the final escape from its constraints. In this region of the story, the moon base begins to change from a point into an area. Tracks in the dust start to matter. Nearby ridges, equipment fields, and science sites become linked by routine travel. Motion becomes regular rather than exceptional. The Lunar Terrain Vehicle embodies this change. It does not make the lunar surface easy, and it does not remove the hazards of distance, cold, dust, or shadow. What it does is simpler and perhaps more important. It gives the base a practical radius of work. Within that widening circle, the outpost begins to behave less like a single shelter and more like the centre of a living surface operation. Beyond the first ring of the local driving around the outpost lies a deeper kind of movement. This is not the short outward reach of an unpressurized rover, where the crew remains fully dependent on the base camp for immediate return. It is mobility with shelter inside it. In the inward structure of how NASA will build a moon base, this next region is the mobile habitat, often described as a pressurized rover. The idea is simple in outline and profound in consequence. Instead of treating every excursion as a brief journey from a fixed home, the base sends out a smaller home on wheels. The vehicle becomes a temporary living space, a workspace. and a protective shell that allows human presence to move farther across the lunar South Pole than short surface trips could allow. A pressurized rover differs from the Lunar Terrain Vehicle in the most basic way possible. It contains an internal environment where astronauts can live and work without remaining in constant external exposure. Pressure here means the interior holds breathable air at controlled conditions. Much like a habitat module or spacecraft cabin, this does not make the vehicle luxurious or spacious in an earthly sense. Volume and mass remain limited. Every system inside must justify its existence. But the presence of a protected interior changes the logic of surface exploration. A crew can travel for longer periods, rest inside the vehicle, manage instruments, review data, and prepare for work without depending on a quick return to the main habitat after every task. This changes what the moon base becomes, a fixed outpost. Even with power and local rovers, still behaves like a central camp surrounded by short operational loops. A pressurized rover allows the outpost to project human capability farther into the landscape while still keeping that capability organized and protected. The vehicle is not the base itself, yet it acts as an extension of the base's internal life. Air, thermal control, computing, storage, work surfaces, sleeping arrangements, and interface systems travel outward with the crew. In this way, the base begins to occupy not just a permanent site, but a wider territory of repeated human use. NASA has long described the pressurized rover as a mobile habitat for extended exploration. That phrase is important because the vehicle is not only transport, it is meant to support science and human function across larger areas than moonwalks from the base camp would allow. It therefore sits at the boundary between settlement and expedition. The base remains the anchor, but the rover allows human work to continue while physically separated from that anchor for longer spans. In the patient growth of a lunar outpost, this is one of the first true signs of maturity. The settlement no longer merely survives in one place. It starts to send self-contained working life outward across the surface. The needs inside such a vehicle are demanding. A pressurized rover must carry life support systems that maintain air quality, temperature, humidity control, and safe internal pressure. It must provide power for habitation as well as motion. It must store food, water, waste, tools, scientific equipment, medical supplies, and spare parts. It must protect electronics and internal systems from the cold, radiation, dust, and vibration of lunar travel. It must include interfaces that allow astronauts to leave in spacesuits for surface work and then return inside without letting contamination gradually overwhelm the cabin. Every one of these functions is already difficult in a fixed habitat. Packing them into a moving vehicle makes the engineering discipline more severe. Dust remains one of the greatest quiet problems. On a base camp, dust can be managed through procedures, airlocks, cleaning systems, and surface discipline, though never removed entirely. In a mobile habitat, dust must be confronted repeatedly after each external excursion. Suit interfaces, storage areas, seals, and filters all need to limit contamination while allowing efficient work. If the vehicle is to support extended journeys, this cannot be handled as a minor housekeeping concern. Dust control becomes part of the rover's ability to remain habitable from day to day. The same polar soil that preserves the moon's history continues to resist easy human use. The pressurized rover also changes the geography of science. A crew no longer has to choose only targets that lie close enough for an out-and-back journey within tight surface limits. More distant ridges, crater edges, and zones of scientific interest become practical. Sample collection can grow more selective because there is greater time to observe context, compare sites, and revisit promising ground. instruments can be used with more patience. A moving laboratory does not create infinite freedom, but it expands the range of thoughtful fieldwork. For a moon base, that matters because the value of sustained presence lies not merely in staying alive on the moon, but in learning more from it over time. This longer reach also supports the practical evolution of the base itself. Future infrastructure decisions will depend on what the surrounding terrain actually offers. A mobile habitat can help crews study possible routes, resource zones, communication placements, and later expansion sites with greater confidence than short visits allow. It may examine where ice-related operations could be linked to the main outpost, where additional science stations might be useful, or where a safer secondary work area could be established. In this sense, the pressurized rover is not only for discovery, it is also a planning instrument. It helps the base understand its own wider neighborhood. NASA's thinking about a pressurized rover has also included the possibility of remote operation between crewed missions. That capability carries great significance. A vehicle that can reposition itself, support robotic observations, or prepare for later human arrival begins to blur the line between dormant infrastructure and active infrastructure. It gives continuity to the surface campaign even when astronauts are absent. The moon then becomes less dependent on uninterrupted human occupation in order to remain operationally alive. The rover becomes one of the first surface assets that can keep the base's influence moving through time as well as through space. There is also an international dimension to this concept. NASA and Japan have publicly advanced cooperation related to a lunar pressurized rover, showing that this mobile habitat is not only a technical object, but also part of the broader partnership structure of Artemis. That matters because a permanent lunar presence is unlikely to emerge from one nation or one agency acting alone. Shared systems, shared services, and shared operational standards make the architecture more resilient and more capable. A pressurized rover developed through partnership fits the wider logic of Artemis, where long-term presence is built through linked contributions rather than through a single isolated effort. Still, the pressurized rover does not free the crew from all dependence. It must recharge, be maintained, communicate reliably, and return to the broader support system of the outpost. Its life support margins remain finite. Its route planning must remain disciplined. In an emergency, distance is still serious. The moon does not become forgiving simply because a vehicle carries an interior cabin, yet the change is real all the same. With a mobile habitat, the human sphere of safe, productive work grows larger and calmer. A journey that would once have been a risky sprint from base becomes a managed expedition with room for thought, sleep, and continued observation. In this region of the story, the moon base takes on a new form. It is no longer only a fixed cluster of habitats, power lines, antennas, and nearby rover tracks. Part of it now moves. Part of its shelter rolls across the dust and carries daily life into the wider polar landscape. The pressurized rover becomes the first traveling expression of permanence, a sign that the outpost is confident enough to send protected human presence beyond its immediate walls. Through that moving habitat, NASA's lunar base begins to act less like a camp at one point and more like the center of a living territory that can be explored, understood, and gradually made familiar. At the center of all this widening motion lies the place where human presence must remain stable when the driving ends and the work outside pauses. This is the habitat itself, the pressurized living core of a moon base, along with the life support systems that keep its interior fit for human life. By this stage in the inward path, the story has moved from orbital access to polar terrain, from light and resource potential to local and travelling mobility. Now it reaches the enclosed human environment that turns repeated visits into sustained occupation. A habitat on the Moon is not simply a shelter from weather in the earthly sense, because the Moon has almost no atmosphere and no weather of that kind. It is instead a barrier against vacuum, radiation, dust, temperature extremes, and isolation. Inside it, the most ordinary conditions of life must be manufactured and maintained. Pressure is the first requirement. Human bodies are adapted to a narrow range of external conditions, and the lunar surface provides none of them. A habitat must hold a stable internal atmosphere, meaning air at the right pressure and with the right balance of gases for breathing. This may sound basic, but on the Moon it is a continuous engineering act. Walls, hatches, seals, windows if present, docking interfaces, and airlock systems all become part of the same responsibility. A tiny leak that would be unimportant in many Earth settings becomes serious in vacuum. The structure must therefore be strong, carefully monitored, and repairable. It must also tolerate repeated cycles of use, connection, and possible expansion as new modules arrive over time. Air quality is more than the presence of oxygen. Inside a habitat, carbon dioxide must be removed, humidity must be controlled, trace contaminants must be filtered, and airflow must keep all areas safe and usable. This group of systems is often called life support. A life support system creates and preserves habitable conditions by managing air, water, temperature, and waste. The phrase sounds compact, but the work it names is constant. Every breath changes the internal atmosphere. Every activity adds heat, moisture, and particles. Every meal, cleaning task, maintenance procedure, and suit return affects the closed environment. A lunar habitat cannot rely on opening a window or venting casually to the outside. It must treat every internal condition as something measured and governed. Water is part of this same closed logic. Astronauts need it for drinking, food preparation, hygiene, and the function of certain systems. Carrying all water from Earth would be possible for short missions, but a base aimed at repetition and growth benefits from recycling. Recycling means cleaning used water so it can serve again. Moisture from breath, sweat, hygiene, and other processes may be captured, processed, and returned to use. Wastewater does not simply disappear. It becomes part of the habitat's internal cycle. On Earth, such cycles are often hidden within large public infrastructure. On the Moon, they occur at the scale of the outpost itself, where every litre matters and every loss increases dependence on cargo from Earth. Thermal control is equally central. The Moon offers no protective air blanket to soften temperature changes. Sunlit surfaces and shadowed surfaces may differ sharply in temperature, and the exterior of a habitat will feel those contrasts. Inside, however, equipment and people need a narrower range. Electronics, batteries, stored supplies, and human bodies all operate best within controlled thermal limits. A habitat must therefore reject excess heat when systems and sunlight add too much, while preserving warmth when the outside environment turns deeply cold. Pipes, radiators, insulation, internal circulation, and active control systems become the unseen climate of the base. A room that feels calm to its occupants is the result of continuous energy and regulation. Volume inside the habitat is limited, yet volume matters greatly for health and function. A base cannot simply be a hard shell with barely enough room to sit and sleep. Crew members need space to work, move, store tools, prepare meals, maintain equipment, exercise, and rest. They also need some degree of order, because disorder grows quickly in small closed environments. Storage therefore becomes a structural principle rather than a convenience. Every surface and compartment must justify its purpose. Supplies need to be accessible without creating clutter. Emergency equipment must remain reachable. Waste must be contained. Scientific work must fit alongside daily living. On the Moon, interior design is not decorative, it is part of survival. Airlocks stand at the boundary between internal life and external work. An airlock allows astronauts to move between the pressurized interior and the vacuum outside without depressurizing the whole habitat. It also becomes one of the main battlegrounds against dust. Suits returning from the surface bring contamination on boots, joints, gloves, and outer layers. If that dust is allowed to spread freely through the habitat, it can damage equipment, burden filters, and reduce long-term habitability. The airlock must therefore support procedures for suit handling, cleaning, inspection, and transition. In some concepts, suits may remain partly or fully outside the main volume through suit port-like arrangements, though the exact operational approach for a future moon base remains subject to evolving design. What is clear is that the habitat must defend its interior from the surface as much as it opens toward it. Radiation protection adds another layer to habitat design. Without Earth's thick atmosphere and strong magnetic shielding, astronauts on the Moon face increased exposure to solar and cosmic radiation. Short stays can manage this risk more easily than long ones, but a base intended for repeated occupation must still treat it seriously. Habitat materials provide some shielding, and local lunar regolith may eventually be used as additional protective cover around parts of the structure. This possibility is scientifically plausible and often discussed, but its exact implementation in an Artemis base remains uncertain and depends on the maturity of surface construction methods. Even without full regolith shielding, the habitat will need strategies for safer areas inside, storm response procedures, and material choices that help reduce exposure over time. The habitat is also where time becomes human again, outside. The lunar environment is governed by route plans, light geometry, terrain hazard, and strict task sequencing. Inside, a base must restore patterns of eating, sleeping, exercise, hygiene, planning, and recovery. These are not luxuries. Human performance depends on them. A crew that cannot sleep well, maintain health, and find moments of quiet becomes less capable at every other task. For a moon base, life support therefore includes mental steadiness as well as air and water, lighting schedules, acoustic control, interior arrangement, privacy to the extent possible, and routine all influence whether long stays remain sustainable. Because Artemis is expected to build presence step by step, the first habitats may be modest and mission-oriented rather than fully permanent in the ordinary sense. They may begin as lander-based or deployable systems that support limited stays and then grow through later additions. Over time, modules may increase living volume, storage capacity, and operational resilience. This gradual pattern matters because a moon base is not likely to appear first as a finished village of large connected structures. It is more likely to become a base by accumulation, with each new element reducing strain and increasing capability. The habitat therefore begins as a necessary refuge and slowly becomes the organized center of a larger settlement. Life support determines the pace of that growth. A base can only expand as far as its ability to maintain habitable conditions allows. More crew means more air processing, more water recovery, more food storage, more waste management, more heat, more power demand, and more maintenance. In that sense, the habitat is not a passive container into which operations are placed. It actively defines the scale of human presence that the moon can support at any given stage. If transport opens the route and mobility widens the field, the habitat decides how much human life can remain there with confidence. At this inward point, the moon base becomes unmistakably human. It is no longer only routes, vehicles, sunlight, and engineering possibilities spread across the polar landscape. It becomes an interior with breath, warmth, routine, and protection. The habitat gathers all the outer systems into one enclosed result, a place where the vacuum stops at the wall and life continues within. NASA will build the Artemis Moon Base by learning how to make that fragile interior durable enough to return to, depend on, and expand. In the end, the true center of the base is not the machinery outside it, but the small controlled world inside where human presence can endure. From the protected interior of the habitat, the next inward layer is the act of leaving it. This is the region of spacesuits and surface work, where the moon base meets the lunar environment directly through the bodies, tools, and repeated routines of the astronauts themselves. A habitat may preserve life, and rovers may extend movement, but the base only becomes productive when people can work outside with enough safety and precision to build, repair, inspect, sample, and adapt. On the moon, that exterior labor is never casual. The ground is abrasive, the light is difficult, the vacuum is total, and every minute beyond the airlock draws on carefully measured reserves. In this part of the base, human presence is narrowed into a portable life support system worn on the body and turned outward toward useful work. A spacesuit on the moon is not clothing in the ordinary sense. It is a personal spacecraft. It surrounds the astronaut with pressure, breathable air, temperature control, and a barrier against dust, radiation, and vacuum. It also carries communications, power, cooling, and the systems needed to remove carbon dioxide from the breathing loop. The astronaut does not merely wear protection. The astronaut enters a small engineered environment that must remain reliable while bending, climbing, lifting, driving, and using tools. This is why surface work on the moon always begins with the suit itself. If the suit is uncomfortable, hard to move in, difficult to maintain, or vulnerable to dust damage, the entire outpost becomes less capable. Movement is one of the first demands placed on a lunar suit. Apollo demonstrated that work on the moon is possible, but it also showed how tiring and restrictive spacesuits can become during repeated activity. Artemis aims to improve mobility because the South Pole environment requires longer, more varied work than short equatorial visits did. Astronauts may need to climb modest slopes, enter and leave rovers, handle instruments, set down cables, inspect hardware, and collect geological material from awkward ground. A suit that resists bending at the waist, shoulders, knees, or gloves turns every task into extra effort. Over time, that effort reduces the amount of useful work that can be done in one excursion. The suit must therefore support the body as a working system, not merely keep it alive. Gloves matter especially because lunar work depends on the hand. Fine motor control is harder in a pressurized glove than with a bare hand on Earth. Gripping tools, fastening connectors, opening storage cases, collecting samples, brushing dust, and operating controls all become slower and more demanding. If the glove design is poor, hands tire quickly and errors become more likely. For a moon base, where repeated outside work is part of daily function rather than a rare event, this detail becomes central. It affects not only comfort but productivity. Tools, suit gloves, and work procedures must be designed together so that real tasks can be completed without turning each operation into unnecessary strain. Surface work also depends on portable life support. the suit-mounted system that manages breathing, cooling, and internal conditions. On the Moon, an astronaut's working time outside is limited by consumables such as oxygen, cooling capacity, and power, as well as by fatigue and route planning. These limits shape the rhythm of every excursion. A repair task must be estimated before the astronaut goes out. A route must be selected with time for return. Sample collection cannot continue without regard for remaining resources. In this sense, the lunar surface is not merely a workplace. It is a workplace with a built-in clock. Every task is performed under a quiet countdown carried on the astronaut's back. Dust remains one of the strongest influences on suit design and surface routine. Lunar regolith clings to surfaces, abrades materials, and works into seals and joints. Boots grind it, gloves touch it constantly. Kneeling, climbing, or steadying a body on the surface brings the suit into repeated contact with it. Over many excursions, this contamination can threaten suit performance unless managed carefully. Surface work therefore includes brushing, inspection, cleaning discipline, and thoughtful handling of tools and suit interfaces. The spacesuit is not separate from the dust problem. It is one of the main places where that problem becomes personal and immediate. The South Pole adds visual complexity to every task. Low-angle sunlight creates strong glare in one direction and dense shadow in another. A rock, cable, or tool may be hard to judge against that contrast. A slope may appear gentler or steeper than it is. Surface work therefore depends on visors, lighting aids, route marking, and careful crew awareness. Vision on the Moon is not only about brightness. It is about interpreting a landscape where the usual cues of depth and texture are altered. This affects even simple activities such as setting equipment down, approaching a lander, or walking around a fixed structure. The astronaut's labor must remain slow, deliberate, and methodical because the environment punishes haste more readily than it rewards speed. A moon base requires many kinds of outside work. Some tasks are scientific. Astronauts may collect rock and soil samples, place instruments, observe surface textures, or examine volatile-bearing ground. Some tasks are operational. Power systems need inspection. Cables may need connection or repositioning. Antennas may need checks. Dust may need to be cleared from important surfaces. A vehicle may require maintenance. Landing areas may need monitoring. Over time, there may also be early construction tasks, such as arranging materials, preparing local ground, or positioning protective barriers. None of this work is dramatic in isolation, but together it forms the lived routine of a functioning base. A lunar outpost is built not only by missions and hardware deliveries, but by repeated hours of suited labor outside the habitat wall. Because surface work is demanding, procedures become part of the infrastructure. Checklists, timing plans, buddy systems, route plans, emergency protocols, and tool preparation all help reduce risk. The calm appearance of a successful lunar excursion depends on extensive discipline before the airlock opens. On Earth, people often separate planning from labor in their imagination. On the Moon, planning is part of labor. The base survives because the work is prepared in advance and carried out in a measured way. A misplaced tool, a poor route estimate, or an overlooked suit issue can matter more than the size of the task itself. Rovers support this labor by reducing unnecessary physical burden. The Lunar Terrain Vehicle can bring astronauts to work sites with their tools. While a pressurized rover can extend the reach of more complex operations, yet the last meters of any task still belong to the suit and the person inside it. A sample must still be lifted, an instrument must still be placed, a connector must still be joined by hand or with a guided tool. This means that even in a technologically supported moon base, human exterior work retains great importance. The machines widen access, but the suit remains the direct interface between human intention and lunar reality. Training on Earth therefore remains part of the lunar base even when far away. Astronauts prepare for surface work through geology practice, suit operations, tool handling, mobility exercises, and simulated procedures in analog environments. These preparations cannot reproduce the moon perfectly, yet they help shape movements and habits that matter later. When the astronaut works outside on the South Pole, the knowledge carried into that motion is partly lunar and partly terrestrial. The base is built through this blend of remote preparation and local execution. As Artemis develops, spacesuits themselves are expected to come through a model that involves commercial partnership rather than only direct government provision. This follows the wider architecture of the program. It also reflects how central suit performance is to long-term presence. A moon base needs suits that can be maintained, upgraded, and used repeatedly as part of a sustained system of operations, not merely as equipment for symbolic excursions. Reliability, repairability, and practical work performance matter as much as survival. On a working outpost, the suit is not ceremonial, it is daily machinery. In this inward region, the moon base meets the human body at its most vulnerable and most capable point. Inside the suit, a person carries a pocket of Earth-like life into an airless world and uses it to perform useful labor on hostile ground. Every cable checked, every sample gathered, every tool handled, and every panel inspected depends on that temporary moving shelter. The habitat may be the center of life, but the spacesuit is the instrument that lets life step out and act. NASA's Artemis Moon Base will only become real through these repeated outward steps, where careful human work transforms survival into operation and operation into settlement. After the human body has gone outside in a spacesuit and learned to work with the moon rather than merely stand upon it, the next inward layer is the material beneath those boots. This is the stage where the outpost begins to ask whether the lunar surface itself can contribute to survival. The idea is often called using local resources, or in more technical language, in situ resource use. The meaning is simple. Instead of carrying every useful material from Earth, a moon base tries to obtain some of what it needs from the place where it stands. At the South Pole, this possibility is tied above all to water ice in cold traps and to the widespread regolith that covers the surface. Together they offer the first prospect that the moon might serve not only as location but as supply. This idea matters because transport from Earth remains expensive in mass, energy, and mission complexity. Every kilogram launched toward the moon must be built, tested, lifted from Earth's gravity, guided through space, landed safely, and protected after arrival. If even a small fraction of needed material can be obtained locally, the burden on that long chain decreases. Yet a realistic moon base cannot begin by assuming that the moon will generously provide everything it requires. Local resource use is a gradual possibility, not an instant transformation. The first role of lunar materials is likely to be modest and specific. Over time, if methods prove reliable, that role may grow. Water remains the clearest example. If ice near the South Pole can be extracted in useful amounts, it can support several needs at once. Water can be consumed directly after proper treatment. It can support hygiene and certain habitat functions. It can also be separated into oxygen and hydrogen. Oxygen matters for breathing. Hydrogen and oxygen together are of interest because they can be used as propellant ingredients if the full chain of production, storage, and handling is developed. This possibility gives lunar water a special status. It is both a life support material and a chemical resource. Even so, the gap between known presence and routine use remains large. The base cannot depend on water until systems exist that can reliably locate, collect, process, purify, and store it. Extraction begins with prospecting. Prospecting means identifying where the material is, how concentrated it is, and how difficult it is to obtain. Remote observations from orbit provide important guidance, but they do not replace measurements on the ground. A cold trap that appears promising from above may contain ice in a form that is difficult to exploit. Concentration may vary sharply over short distances. Access may be hindered by darkness, cold, slope, or loose soil. This means the base must first learn before it can harvest. Robots, instruments, test excavators, and small processing demonstrations are likely to come before any large-scale use. In this phase, lunar materials are not yet supplies. They are targets of investigation. If the ice is mixed into regolith, the process becomes more demanding. Soil must be dug up, moved, heated, and processed so that water can be released and captured. That requires machinery, energy, and time. It also produces wear. Excavation on the Moon means working in dust, cold, and reduced gravity with limited maintenance support. A machine that functions well in a test environment on Earth may behave differently after long exposure to abrasive regolith and repeated thermal cycling on the Moon. The base must therefore judge local resource use not only by scientific possibility, but by practical cost. A deposit is valuable only if the energy and effort required to use it do not overwhelm the benefit. Regolith itself may become useful even apart from ice. It is abundant, and that abundance invites thought about construction and protection. Lunar soil can in principle be shaped, compacted, sintered by heat, or used as covering material around habitats and equipment. Sintering means heating loose grains until they bond together without fully melting into a liquid state. This process has attracted attention because it might allow landing pads, roads, bricks, or protective surfaces to be made using local material rather than imported construction mass. It is a plausible concept supported by laboratory study, but its practical application on the Moon remains a developmental question. The exact machinery, power demand, durability, and operational pace of such methods are still uncertain. A future Artemis base may experiment with these ideas, but it cannot treat them as already mature. One of the more immediate possible uses of regolith is shielding, because radiation exposure is an ongoing concern on the lunar surface. It is reasonable to consider whether local soil could be piled or placed around habitats, shelters, or storage areas to increase protection. Regolith is heavy, and mass between astronauts and radiation can help reduce exposure. The principle is sound. The challenge lies in moving and positioning enough material with the limited machines available in the early phases of a base. A larger, later outpost might make greater use of local soil for this purpose. An early outpost may only begin with modest demonstrations or partial protective arrangements. Again, the pattern is gradual. Local use begins where it is simplest, and grows only as tools and confidence improve. Oxygen extraction from regolith is another long-considered possibility. Lunar soil contains oxygen bound chemically within minerals, especially in oxides of silicon, iron, aluminium, and other elements. The oxygen is present, but it is not available for breathing until released through industrial processing. This is technically possible in principle, yet it is far more complex than merely finding free oxygen. High temperatures, reaction systems, and robust processing equipment are required. Such methods may become important one day, especially for larger-scale lunar industry, but for an Artemis base they remain part of a longer horizon, rather than an immediate operational certainty. The base must not assume that because oxygen is locked into lunar minerals, breathable air will be easy to produce from dust. The chemistry allows the possibility, but the engineering challenge remains substantial. Construction with local materials also faces the problem of standards. A habitat wall brought from Earth is built to known specifications and tested before launch. A structure made partly from lunar material must prove that it can bear load, resist cracking, tolerate thermal extremes, and interact safely with other systems. This is a slower road because reliability matters more than novelty. On the Moon, a failed wall, cracked slab, or unstable berm is not merely a repair task. It can threaten the whole rhythm of operations. Therefore, local material use must proceed with caution and measurement. Demonstration comes before dependence. Even when local resources do not yet support full industrial use, they can still shape the base in smaller ways. Landing areas might one day be stabilized with processed regolith to reduce dust scattering. Protective berms may be raised around certain installations. Resource maps made by prospecting vehicles may influence where later habitats, power systems, or extraction zones are placed. In this sense, the use of lunar material starts affecting the base before large-scale production begins. The outpost becomes more attentive to the ground as a working partner rather than as a passive surface. This stage also changes the psychological meaning of settlement. A human outpost built entirely from imported supplies remains dependent in the most absolute way. It survives only by continued delivery from afar. Once local materials begin to enter the life of the base, even in narrow roles, the relationship changes. The settlement becomes less like a sealed package dropped onto another world and more like a place beginning to engage with its environment. That change should not be exaggerated. Artemis will not arrive and rapidly become self-sufficient, but even partial use of local water, local shielding, or locally processed surfaces would mark an important shift in how a moon base sustains itself. The scientific discipline here is restraint. Observations indicate promise, experiments suggest pathways, and engineering studies outline possible methods. Yet uncertainty remains at every step: the concentration of accessible ice, the cost of extraction, the maturity of processing systems, the durability of products made from regolith, and the balance between local effort and imported supply. A realistic base plan accepts these uncertainties openly. It uses local resource development as an expanding frontier of capability, not as a guarantee. In this inward layer, the moon becomes more than destination, more than terrain, and more than hazard. It becomes possible material. The dust that once seemed only abrasive may become shielding or structure. The ice hidden in polar darkness may become water, air, or fuel support. NASA's Artemis Moon Base will move toward permanence not by escaping the moon's conditions, but by learning, cautiously and step by step, how some of those conditions can be turned to use. That conversion from obstacle to resource is one of the deepest transitions in the making of a true outpost. Once the outpost begins to draw limited value from the lunar ground itself, the next inward layer is the scientific work that unfolds within the territory the base can regularly reach. At this stage, the moon base is no longer only a structure for survival or a machine for logistics. It becomes a working field station. The South Pole region offers questions that cannot be answered fully by brief visits alone. Its geology, its cold-trapped volatiles, its ancient impact structures, and its unusual light environment all reward repeated observation. A base near this region allows science to become systematic rather than opportunistic. The difference is important. A short expedition collects what it can before leaving. A base returns, compares, revisits, measures change, and places new findings into the context of earlier work. This deeper scientific rhythm begins with geology. The Moon preserves a long record of solar system history because it lacks the atmosphere, rain, rivers, and plate tectonics that continually reshape Earth's surface. Impacts remain visible for immense spans of time. Layers of ejected material, broken rock, and weathered regolith hold clues to ancient events. Near the South Pole, the terrain includes crater rims, slopes, basin-related structures, and deposits that may expose material from depth. A moon base gives astronauts and robotic systems the ability to move through this terrain repeatedly, examining not just isolated samples but relationships among sites. A rock gains meaning when its surrounding setting is understood. A slope gains meaning when it is compared with nearby ridges, deposits, and shadowed ground. Sample collection therefore changes in character when a base is present. During short missions, crews must balance curiosity against time, range, and return limits. They may collect material quickly and efficiently, but often with less chance to revisit uncertain interpretations. A polar base allows slower and more structured fieldwork. Samples can be chosen with wider context in mind. Observations from one day can guide a return on another. A puzzling outcrop can be examined again under different lighting or after discussion with specialists on Earth. Instruments at the habitat can help sort results before later excursions. The scientific value of the base lies not only in bringing home more material, but in building a stronger chain between place, process, and sample. Volatiles form another major scientific focus. In planetary science, volatiles are substances that can shift into gas relatively easily, including water, carbon dioxide, ammonia, and related compounds. At the South Pole, permanently shadowed regions may preserve such materials over long periods. Studying them matters for practical reasons because water and other volatiles may support future operations. But it also matters because these materials may record the history of delivery from comets, asteroids, solar-wind interactions, and perhaps interior processes from the Moon's past. A base near the pole makes repeated volatile studies more feasible. Samples from shadowed terrain can be compared with samples from nearby sunlit ground. Thermal conditions can be monitored over time. Small differences that might escape a single mission can begin to form a pattern under repeated observation. This repeated observation is one of the great scientific advantages of a base. Many lunar questions are not answered by one measurement alone. Surface temperatures, frost behavior at the smallest scales, dust transport around hardware, and changes caused by repeated landings all benefit from monitoring over time. An outpost can support instruments that remain active between crew visits, or that are serviced and recalibrated by astronauts. Seismometers, environmental sensors, radiation monitors, and geological stations all become more useful when they are not abandoned to whatever fate follows a single deployment. A base introduces maintenance into lunar science, and maintenance often determines whether an instrument's long record remains trustworthy. Astronaut fieldwork also gains from proximity to robotic support. The Moon Base does not replace robots. Instead, it makes them more useful. Small rovers, prospecting machines, fixed stations, and instrument packages can work alongside the crew and extend scientific awareness into places that are risky, distant, or poorly lit, humans, in turn, can repair, reposition, and interpret the work of those machines. This partnership matters at the South Pole because the landscape is too complex and too varied for one method of exploration alone. Robots can endure patient repetition. Humans can recognize patterns, adapt procedures quickly, and make judgments in the field. A base creates the conditions in which those strengths reinforce one another rather than operating in isolation. The scientific zone around the outpost also becomes a mapped territory. Repeated travel by the lunar terrain vehicle, by pressurized rover, and by suited excursions gradually turns nearby landforms into known places with layered records. Routes are tested, surface properties are compared, sample locations are documented in relation to the broader terrain. Candidate resource sites are assessed again after first inspection. This growing body of local knowledge has a quiet but profound value. Science becomes less dependent on first impressions. The polar landscape, at least within reach of the base, starts to change from a barely known frontier into a studied environment whose details accumulate meaning over time. This accumulation also helps science distinguish the local from the general. The Moon is one world, but no single site represents all of it. Findings from the South Pole may illuminate polar processes especially well, while leaving equatorial questions open. A base makes this distinction clearer rather than blurring it, because crews can return often to the same region. They can define what is characteristic of that region with more confidence. Such clarity matters for comparative planetology, the study of planets and moons by comparing one environment with another. A strong understanding of polar lunar geology and volatiles improves the value of data from other lunar sites and from icy bodies elsewhere in the solar system. There is also a practical science of the base itself. The outpost becomes an experiment in how machines, habitats, materials, and human bodies interact with the lunar environment over time. Dust effects on seals and radiators, wear on rover wheels, changes in landing zones, suit contamination patterns, radiation exposure in different shelter arrangements, and the behavior of a locally processed materials all produce data of high value. This is not science added beside the base. It is science emerging from the act of living and working there. The Moon Base, therefore, studies the Moon in two ways at once, as a natural world and as a setting for sustained human operations. For this reason, scientific work within the base zone does not remain separate from engineering. The same traverse that gathers geological samples may also inspect infrastructure. The same resource survey that assesses ice potential may guide future route design. The same radiation measurements that matter for planetary science also matter for habitat placement and crew safety. Artemis science near the outpost is therefore braided with the practical needs of settlement. This is not a weakness. It is one of the defining strengths of a permanent field station. Knowledge and survival help one another. The South Pole especially rewards this blend because it contains both immediate operational importance and deep scientific mystery. Light patterns affect solar power and thermal conditions. Volatiles affect both life support planning and questions about lunar history. Rough terrain challenges mobility while preserving ancient impact records. A base in this region is scientifically valuable precisely because it is operationally demanding. The work of staying there sharpens the work of understanding it. By this inward stage, the Moon Base has matured into more than a protected foothold. It has become a centre of repeated inquiry. The circle around it is no longer empty ground crossed for convenience. It is a study area with routes, stations, sample sites, monitored shadows, mapped ridges, and remembered observations. Each mission adds thickness to that record. NASA's Artemis Moon Base will build permanence not only through hardware and local resources, but through the patient growth of knowledge in the land around it. Science within the base zone is therefore one of the clearest signs that the outpost is becoming real. A real base does not merely occupy a place, it learns that place in detail, returns to it with discipline, and slowly turns unfamiliar terrain into understood ground. At the deepest inward point of this story, all the outer layers gather into one question. How do repeated missions, scattered hardware, and carefully chosen sites become an enduring outpost rather than a temporary chain of visits? This final region is the base as a whole, not any single part within it. It is the stage where transport, orbit, light, terrain, ice, power, communications, mobility, habitat systems, spacesuits, local materials, and science are no longer separate topics. They become one settlement pattern. NASA does not build the Artemis Moon Base by landing a finished colony in one moment. It builds the base by allowing each mission to leave behind function that the next mission can use, extend, and trust. Permanence grows here through continuity. The earliest form of that continuity is simple repetition. A site that receives one crew and then falls silent is still an expedition site. A site that receives another crew, another vehicle, another delivery, and another layer of support begins to change character. Tracks in the regolith deepen into routes. A landing area becomes a known operating zone rather than an unknown patch of ground. Stored equipment becomes part of future planning rather than leftover mass. Instruments that continue to work after one crew leaves become anchors for the next crew's activity. In this way, a base is not first defined by size. It is defined by whether later missions are able to inherit a useful surface environment from earlier ones. This inherited environment must be organized. Habitats, power systems, communication equipment, rover parking zones, storage areas, scientific stations, and landing sites cannot remain scattered in a careless pattern if the outpost is to endure. Distances matter, dust matters, line of sight matters, safety margins matter. NASA's moon base will therefore emerge as a layout, even if that layout begins in a modest way. Certain areas will be kept clear for landing activity. Certain areas will favour habitation and repeated human movement. Some may be set aside for power collection. Others may support scientific instruments or local resource experiments. The base becomes a place not only because equipment exists there, but because relationships among those pieces are managed over time. This management includes separation as well as connection. Landing systems produce dust and disturbance, so the place where a lander arrives may need to stand at some distance from the habitat core. Mobility systems connect those zones. Power and communication links help hold them together. Science stations may lie farther outward, especially if they are intended to monitor local environmental conditions without too much interference from the busiest parts of the outpost. Resource-related experiments may occupy their own areas if excavation, heating, or processing become part of the campaign. The mature base therefore resembles a small working landscape with distinct functions, not a single compact object dropped onto the moon. Growth also depends on maintenance. A base that cannot repair itself remains fragile no matter how advanced its first hardware may appear. Filters clog, seals wear, wheels erode, batteries age, cables degrade, dust accumulates. Repeated lunar occupation demands inspection, replacement, cleaning, recalibration, and improvisation within careful limits. The crews who arrive under Artemis will not only explore, they will inherit the work of keeping earlier systems healthy. In that sense, One of the clearest signs of a true base is the presence of maintenance as a routine activity. Temporary expeditions focus mainly on achieving a mission before departure. Enduring outposts spend a large share of effort preserving the conditions that make future work possible. Time then becomes layered. One mission may establish a power unit. Another may add greater storage. A later mission may expand the living volume or improve mobility. Another may refine communications, place new science instruments, or begin limited use of local water or processed regolith. The base forms through these additions, but also through what they teach. A system that performs poorly may shape the design of its replacement. A route that proves hazardous may be abandoned for a better one. A landing zone that scatters too much dust may lead to new surface treatment methods. The moon base is therefore built not only by following a plan, but by allowing experience to modify the plan. This is one reason the exact final form remains uncertain. Artemis provides the architecture and the direction, but the surface itself will help decide how that direction becomes reality. An enduring outpost also changes the rhythm of human presence. At first, crews may stay for limited periods with strong dependence on hardware brought from Earth. Over time, if systems become more reliable and better integrated, stays may grow longer and more productive. Longer stays do not only add working hours, they change the nature of presence. A place that supports repeated return becomes familiar. Operations become less dominated by novelty and more by competence. A crew begins work with a memory already present in the site itself. Supplies are where they're expected to be, routes are known, equipment behavior is understood. The base becomes a place of practice rather than only a place of encounter. This maturity also depends on partnership. Artemis is not structured as a solitary national project. Its architecture includes commercial providers, international contributions, and link systems built by more than one organization, gateway, landers, mobility elements, scientific instruments, communications frameworks, and future habitation components all reflect this wider pattern. That matters for permanence because a moon base sustained by many contributors may gain resilience through shared effort, shared standards, and shared investment. At the same time, it also requires coordination strong enough to keep the whole architecture coherent. An enduring base is not only a technical success, it is an organizational success in which many pieces remain compatible over time. Self-sufficiency, however, must be understood carefully. A realistic Artemis Moon Base will not become fully independent of Earth in its early or even intermediate stages. It will still rely heavily on cargo delivery, specialized manufacturing on Earth, replacement parts, mission planning, and broad scientific and engineering support from home. Local resource use may grow. Surface construction may improve. Radiation protection may deepen. Maintenance capability may become more capable. Yet dependence will remain. The honest measure of progress is therefore not whether the base escapes Earth, but whether it gradually reduces the strain of each new mission by preserving and extending capability already in place on the Moon. In this mature form, the base begins to act as a bridge to later exploration goals. The methods learned there will matter for Mars and for other long-duration missions beyond low Earth orbit. Life support reliability, surface mobility, dust control, power management, local resource experiments, radiation response, maintenance practice, and the blending of robotic and human work all carry lessons larger than the Moon itself. Yet the base does not need that broader value in order to justify its existence. Its first purpose remains local and direct. It creates a stable human working presence at the lunar South Pole. Everything else grows from that. What makes the Artemis Moon Base enduring is not monumentality. It may begin with modest volumes, careful schedules, and limited crews. It may appear small against the vast dark and bright contrasts of the polar landscape. But endurance does not require grandeur. It requires reliable return, layered function, and the ability of one mission to leave behind useful order for the next. That is the inner truth of how NASA will build the base. Not by one dramatic act, but by building a place where accumulated engineering becomes accumulated presence. At this final inward point, the whole architecture comes to rest in one quiet image. A habitat stands on chosen ground. Power moves through its systems. Vehicles wait nearby. Instruments work beyond the immediate walls. Routes extend toward shadowed scientific and resource zones. Communications tie the outpost to orbit and Earth. Dust rests on equipment that has already served more than one mission. Inside, human routine continues in a controlled pocket of warmth and air. Outside, the moon remains difficult, silent, and unchanged in its larger nature. Yet within one small region, repetition has created permanence. That is how NASA will build the Artemis Moon Base, by turning return into continuity and continuity into a place that can endure. The outpost settles into stillness without ever becoming truly still. Inside the habitat, air moves through ducts and filters. Heat is guided quietly from one place to another, and stored water waits inside controlled lines and tanks. Tools return to their places. Dust is brushed away as well as it can be. Data rests in memory until the next review. Outside, the polar land remains divided between long light and long shadow. Ridges hold their pale glow near the horizon. Crater interiors keep their darkness. The surface does not soften for human presence, yet it begins to contain a small pattern of repeated life. In that pattern, the meaning of a base becomes simple. It is a place where arrival is no longer the whole purpose. It is a place where people come, work, maintain, learn, leave, and return again. The hardware on the moon starts to remember through its continued use. The routes between habitat, vehicles, power systems, and field sites become familiar. The surrounding ground becomes less anonymous. Each mission adds a little order to the same difficult landscape. The moon itself remains ancient, airless, and patient. Its dust keeps the record of impacts as cold silence. Its shadows preserve materials that sunlight does not reach. Its horizon stays low and stark beneath the black sky. Human presence does not change these larger truths. It makes only a small enclosure of warmth and motion within them. Yet that small enclosure matters because it proves that careful engineering, repeated effort, and measured understanding can hold a human foothold in a place that offers no natural welcome. So the Artemis Moon Base is built slowly, by preserving each gain and carrying it forward. A corridor becomes an orbit. An orbit supports a landing becomes a working site becomes a habitat becomes a settlement pattern. In the quiet of the lunar South Pole, permanence begins not as grandeur, but as continuity sustained one mission at a time.